Okay, welcome to the second part of our tutorial entitled Openness in Radio Access Network Design in 6G, the ORAN concept. After discussing the overall idea about opening the radio access network, in part 2, we are going to go into the details of Open RAN architecture and RAN intelligent controller along with the concepts of RApps and xApps, which will then be followed up by part number 3 and part number 4, where my colleagues were going to go into the details of the design of those kind of applications. So let's move now to the architecture, but before we get into the details of those, let us now speak first about the RAN split options as defined by 3GPP that are then taken by the ORAN Alliance. Okay, so along the standardization within 5G, 3GPP has defined 8 different split options with several sub-options for split number 7. But in our context of Open RAN, we have 2 important splits to discuss, and that are taken into account by the ORAN Alliance from 3GPP world. Split number 2 is the split between the central unit and distributed unit in a place where we have PDCP protocol, so packet data convergence protocol, out of which we have the actual PDCP PDUs handling the IP packets for the user, or RRC messages for the control plane. This is also called higher layer split because it's higher layer in the protocol stack. Whereas on the right-hand side with the distributed unit, we have radio link control, MAC, physical layer, and the RF part. In that case, we are able to have the split with one CU handling multiple DUs using the dual connectivity concept in a manner that is handled by a single base station. In that case, we have modest bandwidth and latency on the front haul. In that case, that's sort of a mid haul rather, for the latency and the throughput on the fiber requirements. And we are able to use it for mobility procedures like dual connectivity or intra-site handover. Now, on the other end, it has a low pooling gain and marginal multiplexing gain because we are not able to handle multiple sites with the same MAC scheduler. The DUs are of higher costs because there is a lot of functionality at the cell site where the DUs are placed at the cell site. And there is a very limited potential for coordinated scheduling. There is another split that was defined by 3GPP along with 5G analysis when they were developing those systems in the beginning. That is called split 7. And the split 7 is basically putting the fiber in between the higher and lower physical layer parts. Now, split 7.2 is a specific point between the IFFT processing and the low physical layer and the beamforming there, and the resource mapping at the high physical layer. So the IQ samples go from CUs to DUs in that particular split, where that is called the lower layer split. It has been adopted by the ORAN. It has not been defined within the 3GPP at that point in time. And that is mostly related to the eCapri interface for the front haul. Compared to split number 2, it has high pooling gain, a lower cost of the DUs, because then the units being placed at the sites does not have to have a lot of functionality there. On the other, and also there is a possibility to use centralized scheduling because there is a single MAC handling multiple radio sites. On the other end, it has very high bandwidth and latency requirements for the front haul. That's basically because we have a lot of data on the front haul interface due to the IQ samples being sent and a lot of control messages for each of the sample, for each of the OFDMA symbol to be placed in between those. So those are the 2 different, let's say, alternatives in terms of how 3GPP analyze those different splits. Now, when going to the ORAN area, we are applying both of them, and we call a higher layer split, and we are using also lower layer split. So splits 2 and split 7.2 are the ones adopted by the ORAN Alliance. Now, in contrast to the 3GPP split 2, which is called a higher layer split, the DU from 3GPP is split further into the DU and the RU, so radio unit that is placed at the base station site. Now, if we speak about the detailed architectural components and the functionality that is placed there, on the left-hand side, we have the control plane and the user plane of central unit. So on the left-hand side, we have central unit with non-real-time functions, managing the connection, managing the radio bearers, using the functionality like handover, server selection, dual connectivity, and functions like that. On the user plane, we have the data encryption, data integrity protection, header compression at the user plane side. So again, in contrast to what we just saw, the CU is also split into user plane part and the control plane part. That is standardized with 3GPP, with the E1 interface between control plane and user plane within the centralized unit. And then we have F1C and F1U. Accordingly, that is connecting it to the distributed unit. The distributed unit handles radio link, control MAC, and high physical layer, including functionality like scheduling, MCS adaptation, so modulation coding scale adaptation, power control, timing advance, carrier aggregation, and functionality like that. And then on the physical layer, we have scrambling, multiplexing, error correction, and all those aspects related to the physical layer at the higher level part. And then the radio unit takes the lower part of the lower layer of the physical layer together with the RF, so radio front end, including the beamforming, MIMO processing, FFT, so the whole OFDMA processing, and then we have the eCapri protocol that is defined and standardized within ORAN Alliance. So those are, let's say, the functional split, and those are the interfaces from 3GPP and sort of placing the different elements for the different protocols. Now, if we go directly to the Open RAN as defined by the ORAN Alliance, we have those entities as we just saw. So RRC with PDCP, control plane, user plane, RRC, MAC, and PHY. And then on top of that, we put the functionality, they put the names for the entities that are defined within the ORAN Alliance. So what we have here is that we have CUCP, CUUP that we just saw, we have DU, and we have RU. We saw all of those, but we didn't see the O in front. So O CUCP, O CUUP, O DU, and O RU. That O means this is the ORAN adapted functionality from 3GPP. So this is the central unit with ORAN in front, meaning it has additional functionality to support the ORAN concept, the ORAN architecture. In addition to that, the OCUCP, OCUUP, and ODU are called E2 nodes. The E2 node is called in such a way because over E2 interface, it is connected to the near real-time RIC or a near real-time RAN intelligent controller that is capable to control those entities over E2 interface that is specified by the ORAN Alliance. On top of that, we have the non-real-time RIC that is in the management plane and that over a WAN interface manages the radio system, and the radio access network is composed of OCUCP, OCUUP, ODU, ORU, and the near real-time RIC. What is important here, non-real-time RIC operates with a larger time scales. We are going to discuss that later in that section. Near real-time RIC operates and optimizes the functionality in the actual base station elements in the near real time, so larger than 10 milliseconds, so several hundreds or tens of milliseconds, whereas we still have the real-time control with the scheduling being part of the ODU, with also power control, with modulation coding scheme adaptation, with beamforming operation. All of that is still there. It's inside the ODUs. So coming up again, we have the 3GPP functionality sitting in the ORAN nodes, on top of which we have the new entities, and the O means we have now the CU, so central unit, distributed unit, RU, as defined by the ORAN Alliance. So now let's speak about all those different entities from the nomenclature perspective. We have those with a little bit more details. So starting from the bottom, we have the O Cloud. The O Cloud is basically a cloud computing platform where basically we have exposed the possibility to put all the other entities on top of that. So that's a cloud computing platform to allow implementing the physical nodes to host the ORAN. So those are the physical nodes to host the ORAN functions like the DU or RIC or CU. And in addition to that, of course, it needs some kind of software components to manage that with the OS, with the VM or virtual machine monitor, and also be able to have some kind of orchestration function for basically scaling the resources. So the O Cloud is the, let's say, the physical infrastructure enabling to put the virtual functions from the ORAN architecture. Now then we have the ORU, which is a logical node hosting lower physical function, as we just saw. ODU, which is a logical node hosting RLC, MAC, and physical layer on the lower layer split. And then we have OCU-CP and OCU-UP hosting the central unit functions, so xApp and PDCP and RLC and PDCP functions. So all these blue elements are sort of free GPP defined functionality adopted to the ORAN Alliance specifications, but they are defined by free GPP, maintained by free GPP, whereas the O means they are adopted by ORAN Alliance. Then the orange ones and the yellowish ones are the ORAN Alliance specific functions, including the O Cloud, including the near real-time, non-real-time RIC, SMO, and xApps, RAPs. So then we go to the near real-time RIC. Near real-time RIC is a logical node enabling near real-time control optimization of the RAN elements and the resources via fine-grained data collection. We'll see that exactly in the next section, but let's start here that this is the near real-time fine-grained operation to manage the CUs and DU. And that is basically serving as a platform for xApps, which are independent from the near real-time RIC, developed by third-party providers, or also by the near real-time RIC providers as well. And then so that's the RAN. And then on top of that, we have the management plane with the service management and orchestration, which is basically a system to orchestrate the RAN. That is also including the second part or a second version of RIC that is called non-real-time RIC. Again, this is a logical node enabling non-real-time control optimization of the RAN elements, and that is hosting the RAPs. So it's a platform to host the RAPs. And RAPs, again, similar to the xApps, are just the applications independent of the non-real-time RIC that might be provided by another third party. So in principle, xApps are sort of distributed zone-like things like load balancing or mobility management, whereas RAPs are sort of centralized types of zone of functions or predictions or machine learning engines, or basically to optimize the network on a longer term. RAPs comes from a RAN app to manage the RAN, and xApps, X is anything, but it also relates to optimization of the functions. So now let's have a look at how they are composed together with and how they are connected to each other via the interfaces. So that's the same picture with the interfaces in between. So again, we have the CUs, DUs as shown before. In addition to that, we have O inode B. So that basically means we are capable of connecting over E2 interface also to the near real-time RIC, the LTE base station, to, for example, support non-standalone application for 5G. We have E2 interface to OCU, OCU-CP, OCU-UP, and ODU to manage those. And then we have A1 interface between non-real-time RIC and near real-time RIC. So that's an important aspect. The A1 interface is between the RICs, but we also have the interfaces from the SMO itself to the individual nodes. We have O1 interface to all of the entities except the ORU. ORU has its own interface called Open Fronthaul endplane. And then we also have O2 interface to the OCloud to manage this. We have the interfaces from 3GPP world F1C, F1U, E1, and also NGC, NGU, X1, and X2, and XN. So the typical 3GPP interfaces. And then we have the orange ones, which are ORAN Alliance specific interfaces, also including the Open Fronthaul between the DU and CU, the DU and RU. So now speaking about those interfaces, A1 interface is responsible for managing the near real-time RIC and the RAN through the near real-time RIC using policy, enrichment information, and machine learning model management. We'll speak about the details of the policy and see examples of this. And then the near real-time RIC provides the feedback based on that policy to the non-real-time RIC. Then the E2 interface is the one to use to monitor, suspend, stop, override, and control the RAN. So control the CU, control the DU, control the CU, CP, CPU, UP, and the DU. And it gets the data back and it gets the feedback on how it's progressing as such. So important here is that the A1 and E2 are the control interfaces, whereas O1, Open Fronthaul endplane, and O2 are the xApps. So xApps, which is the failure, configuration, performance, security, registration, and all things related to configuration and management of the different entities. So we have xApps for ORU, we have xApps for ODU, OCU, and near real-time RIC and OE-Node-B, and then we have xApps or management interface from the SMO to the OCloud. So SMO also manages OCloud, for example, to scale in, scale out resources, to switch off, switch on processors or additional memory. So basically the compute power to host then the OCUs and ODUs, where we could put those on OCloud, we can invoke them, we can close them down, we can move them, and that's why we need to have the O2 interface. So what are the different options for implementation of that particular architecture? One of the options is that we have the network disaggregated network function. So basically, this is just one-to-one mapping from what we just saw. Each of that individual element is a separate entity from the perspective of implementation. So a separate software or hardware piece that is then developed or provided by a different vendor. So a different vendor for OCU, a different vendor for ODU, for a different vendor for ORU, a different vendor for near real-time RIC, and a different vendor for non-real-time RIC. And then also it might be, in principle, a different vendor for SMO. Whereas we could also combine them from the standard perspective into several sub-components. Like, for example, we have the OCU, CP, OCU, UP, and ODU as a single software piece here. So that is a possibility that we not have the E2 interface to each individual element, but we have only a single E2 interface towards a collection of them. And that basically means that the E2 interface needs to be flexible to take into account those particular configurations. So there is the same E2 interface independently or what's the configuration. So it needs to address what functionality it is controlling. So from the DU perspective, it could control the scheduler. From the CUUP, it could control the RLC or I don't know, traffic flow in the dual connectivity options. From the CUCP, it could control handover or carrier aggregation adaptation, or all those things related to idle mode management. So all this is sort of enabling the flexibility of how we deploy different things. There are more and more options. Some other examples is that we could also have the near real-time RIC packed together with the OCU-CP and OCU-UP. And in that case, we don't have the E2 interface between those, but we have an E2 interface from that big entity towards the DU. And then yet another option is that we have all the nodes aggregated, which basically means we have the whole base station from a single vendor. most likely from the traditional vendor. And this is where the A1 interface is the only thing that it is showing that we have the let's say, encapsulation within the ORAN architecture. So this is where we control the RAN via the policies and implementing the A1 interface, and of course O1 and O2 for scaling the resources. But we don't have this disaggregation of the function. That's one thing. Second, it's they are all from a single vendor. So there are different options that the standard allows from the ORAN Alliance perspective. Now, those could be then mapped into different scenarios in terms of deployment. So how we map them to the actual, let's say, points of presence. We might have an example, for example, scenario X, where we have multiple cell sites. They are organized and connected to an individual edge clouds locally, and then we have a more central regional clouds, and then we place those functionalities depending on what we want to achieve. So from one side, we have the PNF, so physical network functions that are realizing ORUs, and those ORUs at the cell sites. And then we have OCloud at the edge cloud, and then we have OCloud at the regional cloud. And on those OClouds, we could put the different configuration from the perspective of the actual functionality from the ORAN architecture. Or we could have a different placement of those where we put the CU at the regional cloud. So now, depending on your needs, depending on the latency requirements for your services, you might be putting those functions on the different places. Of course, at the edge cloud, we could also put the near real-time RIC and have everything closer, which means we could achieve better control loop latency if there is a need. But of course, then we might need to have centralization needs, like we want to have a broader scope for the management by the near real-time RIC or even by the RRC control, and that's why we put the OCU also in the central cloud. On the other end, if there is a lot of connections, maybe it's good to distribute it closer to the cell sites, and then we put the CUs closer to the edge, and then we'll handle locally all the users, but we still have a central location for the near real-time RIC. So now, depending on the use cases, depending on the actual deployment needs, those might be placed in different positions, depending if we have a private network somewhere locally in the factory, or that we have macro cells somewhere in the city, then we might place them differently. And also, because of having them on OCloud, because of having a virtual deployment scenario, we could also change that location depending on the, let's say, traffic. So if there is a huge traffic, then we could distribute them. If there is less traffic, then we could have them more centrally, which means that in the different parts of the day, depending on the actual measurements, we could move those entities to the places where it's more optimal from the energy perspective, or from a performance perspective, or from the overhead and signaling overhead perspective. So those are the different options. And then, of course, as before, the implementation could be different depending on the actual vendor that deploys those kind of solutions. Okay, now let's move to the RIC itself. So again, as we spoke, we have the RIC split into two parts. There is a near real-time RIC in the radio part, or the RAN part, and non-real-time RIC in the management plane, so in the SMO. The non-real-time RIC is sort of a composed of the framework itself. We'll see example or the architecture in a second. And then the RApps are a part of it as an external applications, but it serves as a framework for this. The non-real-time RIC provides configuration, management, and analytics, gets visibility to the network, and it's mostly related to non-real-time adaptation based on the AI feeds, and supports the radio resource management or procedure optimization, policy optimization for the RAN. Whereas it's accompanied with A1 interface, that is intent-based interface, providing policy and additional information to the near real-time RIC, which will then be basically a software platform for xApps. So it again, it's composed of the framework and the xApps that we'll speak about in a second, where it enables near real-time control of the RAN elements via fine-grained data collection, as we already spoke about. And the use cases, example use cases for the near real-time RIC are handover optimization, resource assurance, resource control, load balancing, slicing optimization, and elements like that. Near real-time RIC is similar to the non-real-time RIC, equipped with or associated with a single interface for the control, that is E2 interface, that basically allows to individually control the RAN functions through the xApps. What that exactly means, we'll speak about that in a second. And then ORAN interface is also used here to add additional feedback or performance measurements more collectively, more in a statistical manner, more as KPMs from the E2 nodes and from the real-time RIC to the SMO. And then those are then used by the RApps to provide and guide, provide the policies down to the near real-time RIC. Speaking about the control loops and those different functionality, we have here 3 control loops. The non-real-time latency, so much higher than 1 second, so minutes and hours, used for service and policy management, RAN analytics, is within the A1 interface. So here we have policy feedback and policy updates based on the AI ML training and the RApps guidance that are then fed both from the O1 interface, but also with the policy feedback, with external sources for information. So that based on this, based on the traffic load, based on the traffic prediction, it might basically provide some guidance to the near real-time RIC and to the RAN. The near real-time RIC is associated with the near real-time control loop with the latency of tens or hundreds of milliseconds. And this is for the use cases like traffic steering, like quality of service management, like interference management, radio optimization, scheduler, slow adaptation. But the scheduler is then having the real-time actions, and then the scheduling itself is within the E2 node. So the actual real-time actions are taken within the E2 nodes for the optimization. So one more important point here is, depending on the time scale of the radio resource management algorithm, there might be placed on the different locations. Now getting into the RApps and xApps that will then be taken over by Adrian in the third part of our tutorial. What are the differences between them? Well, xApps already, they are associated with near real-time RIC. So they are running in the RAN domain. They are consisting of 1 or more microservices. So they are basically containerized applications. And what is important is that they are independent on the near real-time RIC, can be provided by third party. And even more important is that the E2 interface between near real-time RIC and the actual E2 nodes enables the direct association between the xApp and the RAN functionality. So the xApp, individual xApp, is controlling individual functionality within the RAN. In contrary to the RApp, which besides it's sitting on a different position, it's not controlling individually any function. It's providing the input and the guidance to create a policy. So the xApp is directly controlling the functionality. RApp is sort of even could send and be connected to another RApp. So it provides input to another RApp, for example, and provides the input to the non-real-time RIC framework that creates the policies to control the RAN. So RApp is application designed to run on non-real-time RIC inside the management plane and provides some additional value-added services to create policy-based guidance, and that performs data analytics, uses machine learning training, and recommending reconfiguration towards the RAN. So those are the differences between those. So RApps is sort of the centralized SON-like optimization algorithms, like energy saving, like I don't know, like capacity and coverage optimization, whereas xApps are the faster adaptation loops for the mobility load balancing or traffic steering. So now with this, let's move to the non-real-time RIC and near real-time in a little bit more details. Here we have non-real-time RIC. I'm not going to go into the details. It's much complicated. There is a lot of functionality in there. There are three main groups, and this is what is important to mention here. The blue ones relate to the actual non-real-time RIC. That's within the part of the SMO, and those are the non-real-time RIC framework-like functions to manage the RAPs mostly, and then secondly, based on the inputs from RAPs, to create the messages down to the A1 interface. Now, let's say, pink parts relate to the inherent SMO functionality. So, for example, termination points for the O1 and O2, but also slicing management functions. And then we have the green ones, which are mostly related to the AI/ML workflows, also related to the external communication from external entities to the SMO, like human-machine interface or external AI/ML interface, to get it from external servers or external enrichment information. So those are sort of a bridge towards the external world, and they could be placed either in the non-real-time RIC or in the SMO framework or somewhere in between, or part of those here and part of those there. And what is meant by that is, well, it depends on the implementation. The SMO might be realized differently. The functionality, the most important ones is that we have RAPs that are connected over the open APIs to the non-real-time RIC framework that needs to handle that and create the outputs for the A1 interface. Speaking about the policies, so we spoke about the, let's say, what is coming up down from the non-real-time RIC to near real-time RIC, and those are the policies that are basically representing the statements to a specific UE. So a group of UEs for a slice ID, for quality of service ID, or for a cell ID. So we could group users in a different manners. We could basically control the RAN individually per UE. And then the policy statements provide so-called objectives to realize by the near real-time RIC from the non-real-time RIC. So those kind of adaptations. And here we have some examples, and Adrian and Łukasz will speak about those in details from the implementation perspective. But here is just an introduction to this kind of, we have this example for the A1 policy, where the scope could be, for example, UEID 855 means we are targeting individual UE with the particular policies that it should prefer, that the near real-time RIC should prefer cells 39 and 40 for that UE. And it's forbidden for him to use cell 81, 82, 83, which basically means the near real-time RIC and the xApp there needs to take that into account while placing the user towards a specific cell. So it creates sort of a boundary within which we can operate. And then we have the traffic steering per slice, where it basically says all the UEs within a slice, within that particular quality of service ID, those are the cells that we could use. So basically, and then the near real-time RIC having those information can say, well, this user will be connected to that cell, and that user for that connection will be using dual connectivity. Now, speaking about the RAPs examples, we might have 3 different RAPs, for example, where it basically gets the inputs from the received signal levels, and as an output, it could provide, I don't know, prediction for what the expected received signal level for different cells for the user will be, or what are the current cell utilization in the current state, and what will be the expected future predicted cell utilization. And in the end, that information, what are the location of the user, what is the cell level, received signal level, and cell utilization, what is the expected quality of experience if we move user from cell A to cell B, or if it stays here for predicted time. So the RAP QoE will take the outputs from the received signal level, from the cell utilization, and from the actual measurements to produce some kind of guidance saying, well, the near real-time RIC could now well allocate those and those and those kind of cells. The user could move there because then the quality of experience will be okay there, right? So this is sort of the flow here. Going down to the near real-time RIC is a little bit more detailed in terms of how it is structured in the standard. Near real-time RIC, of course, has the termination points for all the different interfaces. And it also has the part related to the management of the xApps. Now we are speaking about the xApps. So there is an open API for this. There is a messaging infrastructure so that the data, the measurements, they could be shared between the different xApps. The same type of data could be shared between the different xApps. And then there is this config mitigation function, which is a very important entity because it then allows the xApps to be controlled in a manner that we don't have contradicting actions from different xApps, for example, controlling the same handover algorithm. From the E2 interface perspective, what we have here is that we have those different xApps going over E2 interface. The E2 interface is connecting the near real-time RIC to the different E2 nodes. Important aspect is that we need to have the E2 agent implemented at the E2 node so that the xApps could control the actual functionality. And then the second point, which was already mentioned, the individual xApp is controlling individual function within the RAN, right? So we need to have an exposed functionality like the KPM monitor or like handover algorithm or scheduler or slicing management, something that is then exposed over E2 agents that could be provided to the xApps, and then the xApp control those individual functions through the E2 agent. So now when we have the CU and DU, we need to have an E2 agent implemented, and then it exposes the certain functionality that could be controlled by the individual xApp. So an example data that is coming up from the E2 nodes to the near real-time RIC, we have this physical, the measurements per UE, so very high granularity of the data, per UE signal strength, or per UE data radio bearer per flow occupancy, or per UE PRB utilization, or per UE PDCP duplication, or per UE MCS allocation, or per UE number of retransmissions. So the very granular data coming up from the OCUs with the granularity in terms of periodicity of 10 milliseconds or more, so that the near real-time RIC could actually make proper decisions on what to do with a particular functionality. What is important here again is that we have this config mitigation function that is very important here. That's a procedure, the control procedure coming up from the standard. Here you have the reference to the actual standard for this procedure. What is happening is that because of the individual xApp is controlling a particular functionality at the E2 node, it needs to first to ask the control mitigation function to get the permission to proceed with that particular request. So it basically decides, well, I would like to move user A from cell X to cell Y, and then it needs to send that request to the config mitigation function who process that. And then if it's okay, then it sends that to the E2 termination point. If it's not okay, if it doesn't agree, then it sends the reject to the xApp. And then only after this, the E2 termination point sends the RIC control request, so after agree, to the E2 node. And then the E2 node sends the acknowledgement or failure, whether it's performed that action correctly or not. So after it moves user A from cell X to cell Y, it then sends acknowledgement, which then is fed back to the config mitigation function, so that config mitigation function knows, well, that action has been taken, and I need to take that into account before deciding on another handover from another xApp, for example. And then it passes the success information to the xApp so that it knows that it took place. Also, there could be an option that we don't have directly going through the config mitigation function, because of course it invokes a certain delay. And if we don't have config mitigation function, or we only have a single functionality that doesn't have any conflict, there is an option in the standard that it allows to send a direct decision to the E2 termination point without passing through the config mitigation function. That's also an option, but until we have the set of functions that are not conflicting. So for example, we could have only two xApps. One is working on the handover procedure, and another is working on I don't know, slicing adaptation for the scheduler. And until they are not conflicting each other, the config mitigation function could be passed through. Okay, so that would be a short, let's say, story about the details on the xApps and the near real-time RIC, non-real-time RIC, and the architecture itself. So let me summarize again that second part. We were speaking about ORAN Alliance specifically because it defines the architecture and it specifies the entities like OCU, ODU, ORU, near real-time RIC, non-real-time RIC, SMO, OCloud, xApps, and RApps. So a lot of different entities. Most of them are adapted from FreeGPP with additional control mechanism on top. With the new interfaces, the A1 and E2 for control, Open Fronthaul to split the DU and DU into ODU and ORU, O1, O2, and Open Fronthaul M-plane for management. There are 3 control loops: the real-time sitting in the DU, the non-real-time from the non-real-time RIC between 10 milliseconds and 1 second, and then non-real-time control loop for hours or minutes for controlling the radio resources depending on the time scale. And ORAN Alliance allows different implementation options. Different building blocks from the logical perspective could be implemented physically as different entities, composed together or split apart, delivered by different companies or by the same company. RIC provides the functionality to control, to increase efficiency and optimize network performance for optimal user experience. And then we have those 2 RICs. The non-real-time RIC acts as a configuration layer, whereas the near real-time RIC is a software platform for xApps to actually control the individual functionality within the RAN for RAN management and optimization. And with that, I would like to conclude our session or part number 2 for our tutorial. And I would like to encourage you to listen to my colleagues Adrian, who will be speaking about simulation and the details about the use cases, about the different trials and deployments, and also the implementation of an xApp. And then Łukasz, who will also perform a live virtual lab, where he will show the actual implementation of the xApps together with the control via the policies. So with that, I would like to thank you for attention. Thank you for listening, for watching. And if you have any questions, there will be a separate session in the IEEE ICC at the end of the week, where there will be answers to those questions that you have to the different parts. So enjoy the next parts, and thank you again for attention.